we start today's class. As you have seen in the last class, we have been talking about the nano quasicrystals. You already know what are nanocrystals, you already know what are quasicrystals, and we tried to see under what conditions you get nano quasicrystals. That means you have a matrix in which you get these quasicrystals precipitated in a fine form, and we have seen already that some of the mechanical properties can be improved if you can have that kind of a precipitation of nano quasicrystals. One of the conditions which we have talked about is the oxygen. We showed before in the last class that oxygen plays a very important role, and in case of zirconium based alloy particularly, we showed a particular example where without oxygen or with a very small amount of oxygen below a certain critical value, you do not get any of these nano quasicrystals precipitated in an amorphous matrix, but once you have more than a critical value of the oxygen, you see that there is a precipitation. This is what we have shown in the example of zirconium, copper, aluminum system. We have also shown that if you take only zirconium copper, such a thing does not happen, because the atomic configuration is such that unless you have all the three elements zirconium, copper, aluminum, if you look at the atomic sizes, zirconium is a very big atom, copper is a very small atom, and aluminum is an atom which is somewhere intermediate between these two. So, if you have a big atom and a small atom and put another atom which is intermediate size, that is when you get the best type of packing, and what we have seen is icosahedral packing is the densest packing. So, if in the liquid, if you can stabilize the icosahedral packing, that is where oxygen helps. Oxygen goes into the interstitial positions and then improves the packing density, so that the overall atomic packing becomes very dense, and such a dense atomic clusters which are available in the liquid will have the icosahedral type of arrangement of atoms, and such icosahedral clusters, when you quench them rapidly by rapid solidification, they do not get precipitated during the solidification, because the solidification is very rapid. So, they remain inside the glass as clusters, and we know the clusters are always embryos with sizes less than the nuclei, and unless the size becomes equivalent to nucleus size, it will not become the growth will not occur. So, we know that any size of an embryo, unless it crosses the size of a nucleus, the growth will not occur. So, when you have these clusters which are of the size of embryos, that means very small clusters, during the solidification the liquid has all these clusters now, they are very fine clusters, and but when the liquid is being solidified very fast, there is no sufficient time for these clusters to grow, to become nuclei and finally grow into bigger crystals and give you the nano quasicrystals. So, as a result what happens is they remain inside the liquid, and when the liquid is quenched very rapidly, that liquid becomes a glass, but inside this glass you have these clusters remaining. So, you have these nano clusters. I will show you after a little while some of the high resolution pictures which show such clusters. So, these clusters remain inside the glass. So, the glass, though we say it is a random arrangement of atoms, but it will have some short range order. We say that liquid always has a short range order, but in some of these liquids the short range order will have the type of structure which is icosahedral type of structure. For example, I told you before also, if you take a pure aluminum and then take the liquid aluminum, bring the liquid near to the melting point, that liquid which is close to the melting point, it will have a large number of these short range clusters, which will have the same unit cell as that of the aluminum which is going to come out of the liquid, that is the FCC unit cell. Otherwise, how does the liquid know that it has to become FCC when you solidify it? So, all this liquid everywhere you see there will be small clusters, okay. That is why we always say liquid has a short range order, whereas a gas does not have any short range order. So, every liquid has a short range order, and the type of atomic arrangement within that short range order depends on the type of crystal that is going to come out of the liquid and the type of crystal which has the lowest free energy. So, in case of aluminum, I told you before that FCC aluminum has the lowest free energy. As a result, the short range clusters in the liquid of aluminum will always be FCC clusters, and once you bring it to the melting point, if you cool it slowly, at the melting point that short range clusters will become equivalent to the size of the nucleus, and then that nucleus grows, and that is how you get the grains of aluminum which are FCC structure. Same thing happens here. This we are stabilizing the quasicrystalline clusters which are icosahedral clusters by putting elements which densify the whole liquid. Okay. So, you have these clusters inside this liquid which are icosahedral clusters, and these icosahedral clusters you are stabilizing them by putting oxygen into them. If you do not put sufficient amount of oxygen, it cannot densify the clusters to such an extent to get the icosahedral kind of arrangement of atoms, and once you put a critical amount of oxygen you get these clusters. But the problem is now these clusters are so small that because you are cooling it very rapidly, probably if you cool it slightly slowly you may be able to get them, but the growth of these clusters needs some activation barrier. Any cluster for it to grow, because we know from our nucleation kinetics you have this activation barrier always, we say. So, you have this barrier to be crossed for the nucleation to complete. If you are somewhere here, unless you come to this stage, the growth cannot occur. For that you need to climb this hill. So, for doing that you need to provide certain energy. When you are cooling the liquid, you are unable to provide that much energy for crossing this barrier, and hence the clusters will remain in the liquid. And when you start heating it in a DSC or during annealing, I have shown you the examples of zirconium, copper, aluminum, that are zirconium palladium kind of alloys. We have seen a number of zirconium palladium alloys containing copper, nickel, aluminum. So, these are all the cases where there is no oxygen effect, because palladium stabilizes the quasicrystal, and in the previous case of zirconium, copper, aluminum, where we have seen aluminum the oxygen stabilizes these icosahedral clusters. And now, if you are heating this glass which is obtained on cooling of this liquid, there you are providing the sufficient thermal energy for the clusters to start growing, that you are providing this activation barrier, and once you provide this activation barrier, then you start seeing that they start growing, and that is what you have seen in case of zirconium palladium alloys and zirconium copper aluminum with some amount of minimum amount of oxygen. But there are also, I told you, some systems where you get these nano quasicrystals directly by cooling the liquid. One such example is zirconium platinum alloy. What you see here is a zirconium 20% platinum alloy, 80% zirconium and 20% platinum alloy, where if you take this liquid and start cooling it at different wheel speeds, this is what we say melt spinning. We have talked about it, we will talk in more detail when we talk in the next few classes about rapid solidification processing. But at the moment you already know what is melt spinning, where the copper wheel is rotated and the liquid is allowed to fall on that. And if you rotate this wheel at different speeds, 20 meters per second, 30 meters per second, 40 meters per second, what you see is that this XRD peaks of quasicrystal peaks you start seeing. Whereas, if you remember the previous case of zirconium palladium, when you cool it at these speeds, you never get a quasicrystal during cooling, you always get a glass, you get a broad hump. Whereas, the same system, basically zirconium based system, but instead of platinum palladium we are putting platinum, just you replace palladium with platinum. Instead of 70-30 zirconium palladium alloy, now what you do is you take 80-20 zirconium platinum alloy. This zirconium platinum alloy is very close to the eutectic composition. So, we are choosing the deep eutectic composition in this zirconium platinum system and then cooling it, and when you cool it, what you see is that directly icosahedral phase comes out. And if you want to confirm that it is really icosahedral phase, what you do is go to TEM. If you see in the TEM, you see these fine particles, all these particles are quasicrystal. You have almost 100% quasicrystalline particles in this 20 meters per second, and you can see that micro diffraction pattern taken from one individual particle, which shows you the tenfold symmetry. To give you an idea, yes, these are nano quasicrystalline particles, and if you increase the cooling rate, Increasing the wheel speed means what? Increasing the cooling rate. When you increase the cooling rate, what you see is that the size of these particles become very fine. This we already know from our early knowledge in metallurgy, that whenever I use a higher cooling rate, the grain size decreases. Why? How is the grain size related to cooling rate? There is no time for growth. Anything else?
Sir, at a low temperature, diffusion is restricted.
Anything else? One crucial aspect you are missing it.
The critical size of the nucleus is small, and so the number of the nuclei per unit volume is more.
Yes. The nucleation rate increases. Why it increases? You can see here, if I increase the cooling rate, I increase the undercooling. Why? The liquid, instead of solidifying at the melting point, it solidifies at a temperature much below the melting point because of the inertia. There is an inertia in the system that whenever I am cooling the liquid very rapidly, it does not solidify at the melting point and goes below the melting point and starts solidifying, and that is what we call the undercooling. And this is what, if you plot temperature versus time, you see this kind of undercooling. For a pure metal, we draw this kind of cooling curves. We know that this is what is called undercooling delta T, and this delta T is higher the higher the cooling rate, and if the delta T is higher, we know delta T is related to the nucleation rate and also the size of the nucleus. For example, delta T is related to what is called delta G. If the delta T is higher, delta G is higher. Why? Because delta G is shown as delta HF into delta TA by TF. This formula you all remember, I think. In thermodynamics we have talked about it. This is what is the Turnbull's formula for the free energy change of the liquid to solid, where delta H is nothing but the heat of fusion and TF is nothing but the melting point, and delta T is the undercooling. So, the higher the undercooling, the higher the delta G, and this, if you take the R star, which is the critical nucleus is 2 gamma by delta GV. The higher the delta GV, what you see, the smaller the R star. So, if the CR, if the cooling rate increases, the delta T increases. If the delta T increases, the delta G increases. If the delta G increases, the R star decreases. So, you will get fine nuclei, that is one thing. Second thing is, we also know that nucleation rate is nothing but I is equal to exponential, a pre-exponential term multiplied by exponential minus delta G star, which is called the activation barrier for nucleation, divided by RT. This is the delta G star. Here you see, this is the delta G star for nucleation. Everybody who knows a little bit about nucleation, we all know about this, and this delta G star is directly related. There is a inverse relation between this and the delta G. You remember that 16 pi by 3 gamma cube by delta GV square, that is the formula. We all know this from our second year metallurgy itself, second year BTech metallurgy we teach this. So, you know this formula. So, from here you know that the delta G star is inversely proportional to the delta GV square, and if the delta G star decreases, then the I increases, because there is a negative term before this delta G star. So, if R star decreases, then if delta G increases, then delta G star also decreases, and if the delta G star decreases, finally you will see the I increases. That is the nucleation rate. So, you will get high nucleation rate, and because of which you get fine nuclei, large number of fine nuclei. R star is small, I is large, and that is why you see this kind of fine size icosaedral precipitates. But the question now is, why is that in this particular system you get the nano quasicrystalline phase directly during cooling from the liquid. Why is that in zirconium palladium case that you do not get it, but you have to heat it. Okay. To understand this, we have to understand a little bit more. So, to understand this further, we see another system here. This is a zirconium titanium nickel system. It is a ternary system where we see two compositions. One is the titanium 55, zirconium 20, nickel 25. Another is zirconium 55, titanium 25, nickel 20. These two are the two eutectic compositions in the ternary phase diagram. If you look at the ternary, such as titanium, zirconium and nickel, you have two ternaries here somewhere, depending on the particular composition one can find out. One is a titanium rich composition, so comes closer to the titanium end, and zirconium is about 20%. So, somewhere here you will get. So, this is the type of composition you will get. This is one composition, another is a zirconium rich composition, and again nickel is very small here. So, you will have some composition somewhere here. So, these two compositions, which are the eutectic compositions, when you take them and cool them by melt spinning technique, what you see is that if you cool it slowly, you get the quasicrystal. This is the titanium rich composition, and if you cool it fast, 30 meters per second and 40 meters per second, you get a glass. Similarly, here in the zirconium base also, if you cool it slowly, you again get a quasicrystal, and you cool it fast, you get a glass. And interestingly, in case of zirconium titanium based system and zirconium based system, these are melt spun at 20 meters per second, where you directly get a quasicrystal. If you take them, you see very fine sized nano quasicrystals, something like about 50 to 100 nanometer size, and the diffraction pattern confirms that. And similarly, here also you see very fine, this bar is 20 nanometers, you can see here. That means each particle is about 20 nanometers or so, 20 to 30 nanometers. Such fine particles you get, and the micro diffraction pattern again confirms that these are quasicrystals. And another interesting thing also is that you can take this glass and heat this glass in a DSC, you again get a quasicrystal. So, that means here these are the two compositions where if you cool it slowly, you get a quasicrystal. That means, if you are cooling it slowly, you are providing sufficient time for these clusters which are available in this liquid, the icosahedral clusters which are available in the liquid, to start growing and give you quasicrystal. But if you cool it fast, you are not providing sufficient time. So, the clusters will remain inside the liquid, and that liquid will freeze and give you a glass, and this glass, if you start heating it, that will get converted to nano quasicrystal. So, here is an interesting situation where you see both happening depending on the cooling rate. If you do it very slowly, the icosahedral phase comes out. If you do it fast, glass comes out, because there is no time available, because you know, even for the icosahedral phase to come out, there has to be a nucleation and growth. For the nucleation and growth, there is always what is called an incubation period. You have to provide that incubation period. If you do not provide that incubation period, there is no nucleation. So, as a result, if you are cooling it very fast, 30 meters per second or 40 meters per second, that kind of cooling rate, which is equivalent to around 10 to the power 6 or 10 to the power 5 cooling rate Kelvin per second. At such high cooling rates, the liquid is unable to give you the icosahedral nanocrystals. What happens is that liquid will freeze configurationally into a glass. But as I told you before, glass structure is same as that of the liquid structure. So, if there are icosahedral clusters inside the liquid, they will be there inside the glass also, is not it? And now, this glass containing these icosahedral clusters inside this as a short range order, if you start heating this glass, it will give you these quasicrystals, nano quasicrystals. So,
sir, if we cool slowly, then we are getting quasicrystal phase.
Correct.
Sir, whether they are nano phase or simply just.
Yeah, it will be nano only when you have large number of these clusters. Whenever you take a system, particularly zirconium based and titanium based systems, there is a high driving force for the quasicrystal to come out. If the driving force is very high, you can see from here, if the driving force delta G is very high, then the I is very high, is not it, because driving force is related to delta G star and the delta G star controls the I, and delta G also controls the R star. So, as a result, wherever there is a high driving force for the quasicrystal to come out, there will be a fine crystals, large number of them.
Sir, in that kind of systems, then why we cool fast and then heat?
Yes,
Simply cooling slowly.
you can get it, that is what we are demonstrating, but not in all systems this happens. So, the question is why not in all systems this happens. So, that is what the question that we should answer. So, to understand this further, what we have also done is taken this particular liquid like glass and studied it what is called radial distribution functions. I do not know if you have heard of radial distribution functions. Basically tell you about how the atomic arrangement is in a very short range. That means, if you have an atom, how are the nearest neighbor atoms around that atom are located, what kind of atomic arrangement it has. This is what you get from the radial distribution functions. Okay. It is similar to an X-ray diffraction, but a slightly more advanced type of diffraction technique, where you can see this kind of peaks, and peaks give you, for example, the first peak tells you what is the first interatomic distance. That means, if you choose any atom anywhere and then there are a number of atoms around it, identify what is the first nearest neighbor's distance. That means, you draw lines in all directions, take an atom here and then draw lines in all directions. If you start writing in all directions lines, then you, for example, here in the when this line goes in that direction, maybe you find an atom there. In this particular direction you may find an atom here, in this direction you may find an atom here, in this direction you may find an atom here, and here you may find an atom here, because this is a glass. In a glass it is randomly arranged atoms. So, the distance will vary in each direction, and if you take the average of all these first nearest neighbors, what you get is the average first nearest neighbor distance, and this first peak gives you the idea of the average first nearest neighbor distance. And in the same direction, as you keep on going further, you may find another atom somewhere, and again another atom somewhere here, another atom somewhere here, another atom and another atom somewhere here, and take another average of all those second nearest neighbors. What you get is a second peak which corresponds to the second nearest neighbor, and interestingly the intensity of these peaks keeps on decreasing as you go more and more away from that atom. Obviously, because as you go from one atom to a far distance, the diffraction intensity will be lower. So, as a result, you slowly see that particular peak keeps on oscillating, and finally the intensity comes down. What is interesting here is, if you take the amorphous alloy, this is the type of atomic arrangement that you get, and the same alloy, if you try to take and then heat it to a temperature where nano quasicrystal comes out, and take that nano quasicrystalline sample and then do again radial distribution function, you exactly get the same thing. That means what? It means the atomic arrangement in the glass in a short range is exactly same as that of the atomic arrangement in a nano quasicrystalline phase in a short range. That means, there are definitely some short range clusters which are icosahedral clusters. There is no way to directly see them. One way to see them is to look at this kind of high resolution pictures. If you look at this high resolution picture, which is basically of a glass, this is a binary glass, this is a 5 component glass, both are glasses, but what you see carefully is that there is a random arrangement of atoms in this, but you look at small regions like this, look at this small region, there are fringes there. Can you see those fringes there, atomic fringes? For example, here you see some atomic fringes there, the atoms arranged as spots like lattice fringes. That gives you an idea that there is some kind of a lattice there, and if there is a way to really find out a diffraction from there, unfortunately the size is very small. You can see what is this bar is 5 nanometers. That means the small clusters that we are talking of are 2 to 3 nanometer clusters, such fine clusters, and you come here you will see more here. Here you see this is a cluster again, okay, which is shows you the individual atomic planes. Each line means an atomic plane. So, there is a small short range order there. Similarly, you go here, you see another, you see another somewhere here, yes, you see another here, like that. So, the whole glass is composed of these small short range clusters, and these short range clusters, as you can see from the previous radial distribution function, that these are nothing but icosahedral clusters, because there is no way directly to know, because one cannot do micro diffraction from there. They are so small that you cannot really do diffraction from there to get a 10-fold symmetry pattern, but from this kind of an indirect evidence one can get an idea. So, it is clear that in these liquids there is icosahedral clusters, but the question still remains is that if these clusters are there in both zirconium palladium and both in zirconium platinum, why is that zirconium platinum is able to give you directly when you cool it from liquid? Why is that zirconium palladium is unable to give you? To understand this, we should try to compare these two, and what you see is that various parameters which are compared here. One is, what are the phases which form on a slow cooling condition? When you cool it very very slowly under equilibrium conditions, here you get a Zr2 PD single phase, here you get a 3 phase mixture. So, obviously there is no real correlation between these two. Here you get one single phase, here you get 3 phases. So, obviously there is no correlation, and if you go it slightly faster, here you get only amorphous phase, here you get a icosahedral phase, nano quasicrystal. And if you heat it to a higher temperature, the glass, the phase that you get is Zr2 PD, whereas here you get a 3 phase mixture. So, again there is no correlation there. The only way to check we see a correlation is that the delta H mixing, which is tells you what is the driving force for the liquid, heat of mixing is a direct correlation to free energy of mixing, and free energy of mixing gives you an idea of how stable a particular phase is. The delta G which we are talking about so far, the delta G is correlated to this delta H. So, here you have a high delta H, whereas here it is slightly lower. So, that means what? It means that there is a greater driving force for the quasicrystalline phase to form, here there is a lower driving force. If the driving force is higher, then what you see, you go back to your previous calculation, if the driving force is higher, then the activation barrier is smaller for the nucleation. So, as a result, the icosahedral nuclei can easily form even during cooling the liquid when the driving force is very large, whereas here the driving force is not large enough for the nuclei to form, but they remain inside the glass. And when you start heating this liquid, this glass, it will form the quasicrystal. And another important factor for their formation is also what is called the size factor. If you look at the size factor and the delta H mixing, compare both of them, look at all the binary systems of zirconium. Among all the binary systems, these are the only 2 systems with a large negative heat of mixing. All others have very small, less than about 70 or so. So, none of them give this kind of nano quasicrystalline phase either during cooling or after crystallization of the glass. For example, the red color pictures that you systems that you see, zirconium cobalt, zirconium nickel, zirconium copper, which have very small delta H mixing, they have been cooled rapidly, and we try to see what happens to them. They give you glass, for example, zirconium copper gives you glass, and zirconium nickel and zirconium cobalt give you glass, but some amount of crystals are there, and when you heat these things you always get only one single peak. That means there is no nano quasicrystal. And if you look at what are the phases that are forming both after melt spinning and after DSC heating, you will never get any nano quasicrystalline phase. That means what is crucial is this. And if you look at zirconium titanium copper, zirconium titanium nickel, which is this system, in this system the delta H mixing is not really very large, not really highly negative, but what you see here is that there is a crystalline phase in this system which has a crystal structure very close to that of the quasicrystal. These are what are called Frank-Caspar phases. Frank-Caspar are the two people who have discovered these phases. They are called Frank-Caspar phases, and the phase in this system is called Ti2Ni. And if you replace some titanium with zirconium, you get Ti ZR Ni. So, these two phases, which are called the Laves phases, they have a crystalline structure which is very similar to that of quasicrystal. So, it appears that there are two conditions under which you get a nano quasicrystalline phase. If there is no oxygen, if there is oxygen, oxygen stabilizes it, we already know it. In case there is no oxygen, either you should have a large negative enthalpy of mixing which will stabilize the liquid, because whenever there is a large negative enthalpy of mixing you get deep eutectics. We have talked about it earlier. Wherever there is a high driving force for the liquid to form, there is a deep eutectic. So, wherever there is a deep eutectic, the liquid is stable. If the liquid is stable, then the icosahedral clusters inside them are also stable, and so they can easily give you nano quasicrystal. And in those cases where the delta H mixing is high, it is not highly negative, but less negative, okay, that means are closer to 0. In such cases you need to have a Frank-Caspar phase, and that is what we try to see in this system. We tried to revisit the zirconium palladium, and this time what we did was we chose the composition which is a real deep eutectic composition. That composition is 75-25 composition, and when you take that composition and start cooling it, here you see interestingly that if you cool it at even at 10 meters per second, you get a quasicrystal. 20 meters per second, 30 meters per second, at all conditions you get a quasicrystal, and if you cool it very rapidly you get a glass, and that glass if you crystallize it you get a quasicrystal. And you can see from here, this is cooled at 10 meters per second, you get very fine nano quasicrystals about 20 to 30 nanometer size, and you can see the 10-fold pattern here, you can see the 3-fold quasicrystalline pattern.
Sir, is 10 meter per second the cooling rate?
No, it is a wheel speed. Wheel speed can be directly correlated. When we come to rapid solidification processing, I will tell you how to correlate the cooling rate to it. There is a direct correlation. The higher the wheel speed, the higher the cooling rate. Okay? So, we can indirectly say that lower cooling rate, lower wheel speed means lower cooling rate. Okay? So, you can see high cooling rate gives you a glass, and this glass if you crystallize it you get a quasicrystal. So, we can summarize this whole thing like this. Glasses can be divided into two categories. One is a glass which has small delta H mixing, another is a glass which has a large delta H mixing. This means deep eutectic liquids, this means shallow eutectics in the case of phase diagram. Okay? So, both of them can give you glass. But in systems where you have deep eutectic, that means high negative enthalpy of mixing, even if you cool it slowly you can get a glass like bulk metallic glasses, you all know. If the eutectic is shallow eutectic where delta H mixing is small, you need to cool it very rapidly for the glass to form. Okay? So, these are the two types of liquids you can say. One is a easy glass former, which is a high delta H mixing, negative delta H mixing, which is a deep eutectic liquids. Deep eutectic liquids are easy glass formers, and shallow eutectic liquids are poor glass formers. But I will never say they are not glass formers. Every liquid will become a glass, that is what Turnbull has said long back in 1950s itself. Every liquid will become a glass unless the crystallization intervenes. This was a standard statement made, very bold statement long back, about 50 years back. That means unless crystallization comes into picture, every liquid wants to become a glass, because the liquid structure is same as that of the glass structure. So, there is no problem for the liquid to become a glass, only problem is crystallization comes into in between. So, if you can suppress that crystallization, every liquid will become a glass, and it is easy for the liquid to become glass in deep eutectics, it is more difficult in shallow eutectics. And in shallow eutectics also we can divide it into two groups, one without Frank-Caspar phases, one with Frank-Caspar phases. That means those systems where Frank-Caspar phases do exist and those systems where Frank-Caspar type of phases do not exist. Not every phase diagram, every system will have this kind of phases. For example, if I take copper nickel phase diagram, it is a solid solution, there are no intermetallics there at all, but if I take aluminum nickel, there are intermetallics. So, every system is not the same, some systems show intermetallics, some systems show solid solutions, some systems show complete immiscibility, is not it. So, like that some systems have a tendency to show Frank-Caspar phases. What are those? The examples are aluminum manganese and titanium nickel, which show Frank-Caspar phases. So, if you take that kind of a liquid system and look at the TTT type of a diagram, here you take the liquid, cool it rapidly, you get a glass, and that glass if you cool it, if you start heating it, that glass will give you a quasicrystal first and then finally a crystal, because there is a Frank-Caspar phase in that system whose crystal structure is similar to that of the quasicrystal. So, there is a greater tendency for the quasicrystal to form, and the same liquid if you cool it slowly instead of cooling it very fast, that liquid will give you a quasicrystal if you cool it relatively slowly. If you cool it very slowly, you get a crystal. That means, if you cool an intermediate cooling rate, you get a quasicrystal. And if you take the systems where there is no Frank-Caspar phase, there is no another TTT curve for quasicrystalline phase, because there is no Frank-Caspar phase. If there is no Frank-Caspar phase, there is no quasicrystal. So, the liquid if it is cooled rapidly, it gives a glass, and that if you start heating it, you get a crystal, you do not get a quasicrystal in that. So, these are the two systems where in one system you get a quasicrystal either by slow cooling process, intermediate cooling rate, not very slow. If it is equilibrium cooling, ultimately you get only a crystal. Equilibrium cooling always gives you a crystal, because quasicrystal is always a metastable phase. We know that it is always a metastable phase, excepting in a few systems such as aluminum, copper, iron, where we get stable quasicrystals. Otherwise, in most of the systems it is a metastable phase. So, you can see these are the two types of systems under the shallow eutectics. And if you look at this, this particular wherever Frank-Caspar phase is there, the cooling rate that is required for getting a glass is higher. You can see the critical cooling rate, which is indicated by the steepness of this tangent, is higher here when compared to here. So, wherever there is a Frank-Caspar phase, if you cool it slowly, the tendency is to get a quasicrystal. If you want to get a glass, you have to cool it very rapidly. Then come to here. Here also there are two possibilities. One is binary deep eutectics and multi-component deep eutectics. That means, if you choose a binary system with high negative delta H mixing, such as either zirconium palladium or zirconium platinum. Okay. If you cool it very slowly, ultimately you get a crystal, that we know. If you cool it at an intermediate rate, you get a quasicrystal, nano quasicrystal. In zirconium platinum we have seen it already, whereas in zirconium palladium the driving force is not so high to give you a quasicrystalline phase. So, when you cool it, you get a glass first, and that glass, when you start heating it, it gives you a quasicrystal and finally a crystal. But if it is a multi component system, the problem is, in a multi component system there are so many elements, and because of these so many elements the diffusivity is very slow, and because of the diffusivity is very slow, for the nano quasicrystalline phase to form during the solidification, it is very difficult, because the atoms have to come together, form the nucleus, and the nucleus has to grow. For this to happen, it is very difficult during cooling. So, as a result, it is very difficult to get a nano quasicrystalline phase in a multi component systems by cooling. So, always you get a glass, because the TTT diagram is shifted to the right. Why is it shifted to the right? Because the incubation period is very large. Whenever there is a large incubation period, the TTT curve is shifted to the right. That is why in multi component systems the TTT curve is much to the right when compared to binary system. You can see the binary quasicrystalline, this one is to the left when compared to the multi component quasicrystalline, and so it is easy to get a glass. So, if you look at the slope of this critical cooling rate, that critical cooling rate is much smaller for a multi component system when compared to binary system. So, you can get very easy glass forming. So, these are all very easy glass formers, that is why we call them as bulk metallic glasses. And such bulk metallic glasses, if you take, you start heating them, all these bulk metallic glasses have these nano quasicrystalline clusters inside them, because as I told you, whenever you stabilize a liquid, you are stabilizing icosahedral clusters. There are a number of people who have shown that there are icosahedral clusters inside the liquid. All glass forming liquids, particularly strong glass forming liquids, wherever high glass forming ability is there, there you have these icosahedral clusters inside them, and when you start heating them, for example, one example as I showed you, zirconium, copper, nickel, aluminum, there are innumerable number of examples here. You put a palladium here, you put a silver there, you put a platinum there, you put titanium there in this multi component system, all of them give you nano quasicrystal. So, there are so many such multi component systems which on cooling they always give you a glass, because they are easy glass formers. You can never get a nano quasicrystalline phase during cooling, you always get a glass, because even if you cast it by into a normal metallic mold, you get a glass in such alloys. As I told you, you get almost 30 millimeter rods in such zirconium based systems, that means 3 centimeter dia rods. So, very high glass forming ability. So, this is what is a way we can really summarize this whole thing and show what are the real conditions for the formation of these glasses.
Sir, for multi-component system,
We will stop here.
sir, if the cooling rate is less than the critical cooling rate, then why we would get the nano quasicrystal clusters in the class? Because
if it is less than the critical cooling rate, you will definitely end up in this the what is called the nano quasicrystalline phase, but the critical cooling rate itself is so small. For example, if the critical cooling rate is equivalent to that of a sand casting, okay, then it is very difficult to have cooling rate even still smaller than that. So, as a result, you rarely see a formation of a nano quasicrystalline phase, always the liquid will give you a glass, and that glass, if I start heating it, it will first give you nano quasicrystal phase, and then finally it gives you the crystal. And then if you control the temperature and time such that you get a large fraction of these nano quasicrystalline phase, you have now what is called a composite. You have an amorphous matrix and a nano quasicrystalline phase dispersed in this amorphous matrix, exactly similar to an aluminum silicon carbide kind of a composite. So, that kind of composites have much better mechanical properties, and that is why everybody wants to go for such a thing. Frank-Casper phases are basically, you see, we know every intermetallic compound is a complicated intermetallic compound. I have shown you, for example, earlier a phase aluminum zinc magnesium kind of phase, which has almost 91 atoms. You remember, it has a aluminum shell, on that a magnesium shell, again magnesium zinc shell, another aluminum shell, and if you carefully look at those crystal structure, they are all icosahedral structures. So, these are some complicated, there are many simple intermetallics also, for example, NiAl. NiAl is just a BCC intermetallic compound, ordered BCC. Fe3C, we know Fe3C is an orthorhombic structure, but not every intermetallic compound is so simple. For example, we also know Cu3Au or Au3Cu, these are all very simple cubic structures, but there are certain intermetallic compounds where in one unit cell there are many number of atoms, sometimes even 1000 atoms. Such crystal structures are very complicated, and such crystal structures have a tendency to have a very large close packing and get into this kind of structures which are called the Frank-Casper phases. There I told you structures which are called Bunsen type of structures or Frank-Casper type of structures, depending on the type of depending on the person who has discovered, different names have been given. When we were discussing about various crystal structures, we talked about that. Anything else? We will also shortly see some nano crystals which are obtained by from the glass. As I told you, one way to everybody nowadays wants to get composites, not just the glass, not just the quasicrystal, or not just a nanocrystal, but a composite of all these. Okay. We have talked of one type of a composite where you have amorphous matrix and nano quasicrystals. You can also have an amorphous matrix and nanocrystals inside that. Okay. One example is this iron copper zirconium alloy, which is a glass, iron zirconium boron alloy, which is a glass, and put some copper into it. Iron and copper is a system where they do not attract each other. There is a repulsion between iron and copper. So, as a result, there is a tendency for the copper to come out as precipitates. Why? For example, in steels we add copper. Have you heard of any steels where people add copper? Where copper comes out as precipitates and gives you very high strength. Okay, age hardenable. Nowadays people are calling of IF steels, interstitial free steels, where people are adding copper. We also know that in steels we used to add lead. Have you heard of these steels? These are called free machine steels or free cutting steels. Why do we add? Because lead does not dissolve in iron. So, it precipitates as a fine particles, soft particles, and so you can easily machine when it is uniformly distributed. Similarly, if you can distribute copper, so what we have done is taken a glass having a iron zirconium boron kind of a glass, put different amounts of copper. These are all different amounts of copper. 0% copper gives you a glass, and as you keep on increasing the amount of copper, you start getting the XRD peaks of copper. And if you start looking at the TEM with no copper, it is all amorphous. You see the diffraction pattern. When you start adding some copper, very fine precipitates, you can see this is 100 nanometers. So, what you have is around 5 nanometers or 2 to 5 nanometer particles, and then you go to higher, you start seeing bigger and bigger particles coming out, and you go to still higher, you start seeing big particles. And now at this stage one can get rings corresponding to this copper particles, and one can put a diffraction the electron beam on individual particle and get what is called micro diffraction patterns, and to show what is the zone axis and what kind of a particle it is, whether it is copper or not. We can also put electron beam on this and also do what is called EDAX to find out that these are copper particles. So, like that one can depending, these are all, if you look at, they are all cooled at the same speed 40 meters per second, 0% copper, 2%, 10%, 15%, and this is 20%. It is not really percentage copper, in fact it is out of this. So, if you have to find, if you want to know exactly what is the amount of copper in this, you have to multiply 0.2 into 70. So, you will get about 14%. Okay. So, what we have done here is we have varied copper and iron in such a way that the total is 100 here. So, that is how, because the copper gets substituted into iron here. So, that is why we have varied the copper here. And so, you can see we can also get a glass, take a 10% copper alloy, you see 10% copper is this, which have very fine particles, you cannot really see. You see diffraction pattern does not show any copper peaks, copper rings, it is still amorphous. They are so fine that the diffraction pattern is unable to show any rings corresponding to copper. And take such a one and then start annealing it at some temperature and start getting the fine particles. And when you look at the mechanical properties of this, it gives you almost 2 gigapascal strength, a very high strength alloy, these alloys. And one can do different compositions, can be taken, isothermal annealing can be done, different temperatures and timing. This is 573, 673 and 773, all 10 minutes. You can see the particles are very fine at low temperature, particles start becoming bigger when you go to much bigger, and you can see all the twinning inside, the growth twins we say, whenever particles which are embedded in an amorphous matrix, the matrix is amorphous, mind it. If I put a if you carefully observe this diffraction pattern, which is a micro diffraction pattern taken from one of the particle, but you can still see the ring, amorphous ring, which is coming from the matrix. So, these are basically the matrix is amorphous. If I put the electron beam on the matrix, I will get only amorphous ring pattern, and this is corresponding to the individual particles. So, that is how one can find out various particles and see that one can get such nano crystals in an amorphous matrix, nano quasicrystals in an amorphous matrix. One can control the size and distribution of these particles by controlling the temperature and time of heat treatment, and finally control the mechanical properties. For example, we know in age hardening also it is the temperature and time which is crucial to get the best properties, because we know in age hardening there is always a peak in the hardening, what we call the peak aging. If you do less than that, the time, if the aging time is less than that, you get less hardness. If the aging time is more than that, you lose the hardness. So, like that there is always a particular temperature and time where you get the best distribution of these particles. For each alloy, people have started optimizing these conditions, so that one can get the best properties. As metallurgists, we are more concerned about the mechanical properties. These are some of the new advanced materials where one can achieve much higher strength, because if you have a normal composite, aluminum silicon carbide composite, you cannot reach strengths beyond about 500 megapascals. 500, 600 megapascals is the kind of upper limit, but here are the opportunities. Even in a typical aluminum based alloy, one can reach almost 1.5 gigapascals. So, these are some of the real exciting materials, I should say, as far as metallurgists and mechanical engineers are concerned, because one can think of, only thing is how to make them in large quantities and then how to control the process parameters, so that we can make them in large quantities and then compact and then bring them to any particular shapes of our interest. So, and during this processing of compaction and sintering, we should be able to control in such a way that they do not really grow. So, that is another area where a lot of people are working. We will stop here.